Quantum mechanics and classical physics represent two fundamentally different paradigms that describe the behavior of matter and energy in the universe. While classical physics emerged from centuries of empirical observations and mathematical formalism, quantum mechanics revolutionized our understanding of nature at the microscopic scale, challenging classical notions of determinism and causality. This essay aims to provide a detailed analytical comparison between quantum mechanics and classical physics, exploring their theoretical foundations, experimental validations, philosophical implications, and technological applications. Foundations of classical physics. Classical physics, rooted in Newtonian mechanics, describes the motion of macroscopic objects under the influence of forces like gravity and electromagnetism. Newton's laws of motion and universal gravitation provided a robust framework for predicting and understanding the behavior of objects ranging from projectiles to planets. James Clerk Maxwell's formulation of electromagnetism in the 19th century unified electricity and magnetism, introducing Maxwell's equations. These equations describe the propagation of electromagnetic waves, including light, as well as the behavior of charged particles in electric and magnetic fields. The birth of quantum mechanics. At the turn of the 20th century, physicists encountered phenomena that classical physics could not explain, such as the blackbody radiation spectrum and the photoelectric effect. Max Planck's proposal of quantized energy levels and Albert Einstein's explanation of the photoelectric effect laid the groundwork for quantum theory. Quantum mechanics, formulated by pioneers like Werner Heisenberg, Erwin Schrödinger, and Niels Bohr, introduced revolutionary concepts: wave-particle duality, where particles exhibit both wave-like and particle-like behavior; the uncertainty principle, which states it is impossible to simultaneously know the precise position and momentum of a particle; and quantum states and probabilities, where particles are described by wave functions and measurements yield probabilities rather than definite outcomes. Alright, so let's dive into the key differences between quantum mechanics and classical physics. Classical physics adheres to a deterministic worldview, where precise initial conditions determine future states with absolute certainty. In contrast, quantum mechanics introduces probabilistic outcomes, suggesting inherent uncertainty and the role of observation in defining reality. Classical physics applies to macroscopic objects, where quantum effects are negligible due to large masses and energies. Quantum mechanics, however, governs the behavior of particles at atomic, subatomic, and microscopic scales, where wave-particle duality and quantum tunneling are observed. Experimental validations and quantum phenomena. Quantum interference and superposition. Experimental demonstrations, such as the double-slit experiment, illustrate quantum interference phenomena. Particles exhibit wave-like interference patterns, indicating their wave function's superposition state until measured. Entanglement and non-locality. Quantum entanglement, where particles become correlated regardless of distance, challenges classical concepts of locality and separability. Bell's inequalities and subsequent experiments confirm the non-classical correlations predicted by quantum mechanics. 5. Technological applications and quantum technologies. 5.1. Quantum computing and information. Advancements in quantum computing promise exponential computational power by leveraging quantum bits, or qubits, and quantum parallelism. Quantum cryptography offers secure communication protocols based on quantum key distribution. 5.2. Quantum sensors and metrology. Quantum sensors, such as atomic clocks and magnetometers, surpass classical counterparts in precision and sensitivity. Quantum metrology techniques enhance measurements in fields ranging from medical imaging to geological exploration. 6. Philosophical implications and future directions. 6.1. Philosophical debates, realism versus interpretations. Quantum mechanics raises profound philosophical questions about the nature of reality, observer influence, and the interpretation of quantum phenomena. The Copenhagen interpretation emphasizes measurement and wave function collapse. The many worlds interpretation suggests multiple parallel universes for each quantum outcome. Bohmian mechanics proposes hidden variables to explain quantum behavior deterministically. 6.2. Future challenges and unification efforts. Efforts to unify quantum mechanics with general relativity, also known as quantum gravity, remain a significant challenge in theoretical physics. The quest for a theory of everything, or TOE, aims to reconcile quantum mechanics and classical physics under a single comprehensive framework. Conclusion. Quantum mechanics and classical physics represent distinct yet complementary approaches to understanding the universe, each with profound implications for science, technology, and philosophy. While classical physics provides accurate descriptions of macroscopic phenomena and forms the basis of engineering and everyday experiences, quantum mechanics unveils the mysterious realm of particles, waves, and fundamental forces. As scientific inquiry progresses and technological advancements continue to blur the boundaries between classical and quantum worlds, the pursuit of deeper insights into quantum phenomena and their integration into a unified theory remains at the forefront of modern physics.